if in your car you have, or in a car that you've ridden in, you have a length of string and some random object on the end. Let's just hang there. When you are at rest, you'd get something like this, correct? So at rest, or even if you were not accelerating, so you're just tooling down the street, been going in a straight line for a while, I'd expect it to look like this. But then, if the forward motion of your car is this way, and you step on the brakes, doesn't this thing now swing like that towards the front? And it does so, and maybe hits the windshield, maybe not, depends on your car. Or if you're at rest and you're about to take off, doesn't it not swing backwards towards you? Let's say that you are taking off and it's swinging backwards towards you. And you're accelerating with an acceleration of 3 meters per second squared. Not necessarily for very long. This could be just a second or two. Let's say you accelerate forward at 3 meters per second squared. What angle would this make? That's what I want. I want the angle it makes. Now, this is a force problem. I want you to approach this, maybe not knowing how to get to the answer. I want you to approach this because this is a force problem that you should be able to solve if you just apply the series of steps that I've given you. I'm going to say, I'm not sure that you know how to get to the answer, but what I want you to do is recognize that this problem can be solved using forces. There are clearly forces acting on the object. And if you use the series of steps we've talked about with Newton's laws, you should be able to come to some conclusions. Maybe solve the problem. I don't know. Try it. See what you can do. Start with a free body diagram and then apply a coordinate system and then attempt to determine what the net force should be in each direction. Try. Did you start this problem by taking the entire problem and reducing it down to a dot and asking yourselves, first, are there any fundamental forces acting on the object? Are there? Gravity. Okay, we have a start. We have gravity. So I assume you drew an arrow downwards. And we said that this would be mg, or weight. That all right? Is there anything else in contact with the object? The string. All righty. Look good? What would you call this? Tension. Is there anything else in contact with the object? I know I heard some of you talk about air resistance and stuff, but the air in the car is moving with you. It's not moving through the air. So no, I don't think there's any air resistance, and it's definitely not sliding across any surface. I think this is it. Are the forces unbalanced? Yeah, I hope so. Is it traveling with the car? Yes. So if the car's accelerating, is it accelerating? Yes. That's it. The forces should be unbalanced. In fact, what direction is the car accelerating? So there's an acceleration in that direction. I think by definition, or not by definition, by instruction, I will make this the positive x direction. If I make that the positive x direction, this has to be the positive y direction. Have I veered at all from our series of steps? No, not once. Do I have any off-axis forces? I do. I have an off-axis force. I'm going to need to find the components of that force. I suspect there is a component of that force that's upwards, and a component of that force that's to the right. So let's kind of focus. I'm going to go this way and this way, because this is also theta. You all know that that's theta, right?
Yeah.
I'm unconvinced, but I know that all of us have had basic geometry. And I know that you know that if I have two parallel lines cut by a transversal, alternate interior angles are congruent. At least I remember that crap from 8th grade. I hope you all did, because for me, that was like a lot of years ago. And for you, not so many. And you all enjoyed your A's back then, so let's continue. It seems like I have some trig to do. Can you do the trig? Do so. Help me out here. What do I label this force? Thank you, t cosine theta. And what do I label this force? Yeah, it's easier to come up with that one, isn't it? All right. Again, have I veered at all from the series of steps I told you? Not even a little bit. It appears to me like I have now put my components there, so I can get rid of the force that was there before and just focus on the components of that force. With that being said, I'm going to apply Newton's laws now. Net force in the x direction, net force in the y direction. Which one of these is 0, or are they both 0? Y is 0. The object accelerates with the car to the right. So that suggests that net force in the x direction is ma. In the x direction, how many forces do I have? 1. T sine theta equals ma. In the y direction, how many forces do I have? T cosine theta minus weight equals 0. Don't think so. When I originally had this written here, I had it drawn like that, and this is where theta is. I'm pretty much done. I mean, you should be able to tell me now what the angle is. There's more than enough evidence for you to do so. I don't want to wait around, because I know that there's the people who can do it will do it, and people who can't will just sit there hoping somebody else will do it. But there's a clear pathway. If you don't see that clear pathway, focus on what's on the screen right now. I can do a substitution here, which will give me t cosine theta equals mg. And I already have t sine theta equals ma, and you were given that a is 3 meters per second squared. I think you can do substitution here. In fact, you can just divide one equation by the other. T's will cancel, M's will cancel, and you'll get tan theta equals A over G. Who's done this before? Divided one equation by another? Well, you have now. Put it in your notes. You can do this. This is how math works. You can divide both sides of an equation by the same thing. Therefore, I'm dividing the left side by t cosine theta and dividing the right side by mg because they are equal. The m's cancel, the t's cancel. And I'm indifferent to what the answer is, but it's the inverse tangent of 0.3. You'll get an angle. In fact, this is a cheap accelerometer. If you wanted to have a cheap accelerometer when you go to Busch Gardens, you just hang a weight from a protractor. And whatever the angle is, tells you your acceleration. In fact, a shrewd student would realize that 1 g of acceleration would be at 45 degrees. If you want to be a shrewd student, you would look at that. When does this equal 1? All right. Did I veer at all from that series of steps we discussed? I want to point out, even if you don't know exactly what to do, that series of steps should provide you with some context, a place to begin. We're going to try another one. This one will be a little more recognizable by some folks, I hope. We'll see. I'm not sure. Again, the only thing I did was that I lift this up 15 degrees. Drawing arrows down the ramp, but I start with a dot representing the calculator. Did you draw a downward arrow indicating the force of gravity? All right, excellent. It is clearly gravity that's pulling the calculator down. Clearly. But the book is in the way. So if I draw this force, this indicates the force of gravity acting downwards on the calculator. mg. I don't have to write W every time. Is there anything in contact with the calculator? The book. What kind of force does the book apply to the calculator? A normal force. I don't get a choice on how to draw this. I have to draw a force that is perpendicular to the surface of the book. Is that perpendicular? Looks pretty close. Perpendicular to the surface of the book. I'll label that normal. Is there anything else pushing or pulling on the calculator? No. 2 arrows. You're supposed to draw a coordinate system with 2 potential priorities. Priority number 1, in order to align the positive direction with the direction of the acceleration. Does our object accelerate? Yes. Well, I sure better align my coordinate system with the direction of the acceleration, suggesting an alignment that is down the ramp. I will make this the positive x direction. That forces this to be the positive y direction. Have I veered away from any of our set of steps yet? Have we done everything that we said we need to do? Are you doing these? Are you reading what we talked about? I know you're not. Now the hard part here is, where does the 15 go? I don't know why this is so hard for students, but they really don't know whether to put it where I put 1 or put it where I put 2. I know where they want it to be. They want it to be where 2 is, but it's wrong. If the angle of the book gets smaller, isn't mg going to get closer to straight down in the y direction? Isn't the normal force going to go up? Only one of these will get smaller when 15 gets smaller. So that's got to be where the 15 goes. Right there, 15 degrees. If you don't want to try and figure that out using triangles, then I will tell you. the angle of the incline goes between the weight and whatever is aligned with the normal force. I'm giving you instructions. I'm telling you what you should do. I'd encourage you to write it down. Now, my next step is to take any off-axis components and break them up. Any off-axis forces and break them up into components. I will watch as people screw this up. For whatever reason, they don't like to make the triangle correctly, but the triangle should have the right angle against the y-axis like so. I promise that if you are the person who draws this, then your work will be displayed in class. Do we understand each other? I'm not joking. This looks ridiculous to me, but may not look ridiculous to some of you. But the components have to be at a right angle to each other. The red arrow is the actual force. The green arrows are the components. They must be aligned with the y direction and the x direction. So this one needs to be lined up with the x direction so that it makes a right angle with its component. And when I look at that, I see mg cosine theta here and mg sine theta here. Right? The opposite side gets sine and the adjacent side gets cosine. I've now taken my off-axis force and broken it up into components so that I could get rid of my original force and have my components take over for me. First law problem or a second law problem? Second law problem, net force in the x direction equals ma. I forced that to be true by putting the acceleration in the x direction, which means net force in the y direction equals 0. I forced that to be true because I made the x direction the direction of the acceleration. So whoever asked me after class yesterday, why did I make it that way? That's why. So only one of these would have an acceleration. There appears to be only one component of force in the x direction, mg sine theta. And that has to equal ma. In the y direction, I see two forces, normal minus mg cosine theta. That has to equal 0. For anybody who says we haven't taught the homework yet, yes, I have. The homework's been taught. You just didn't see that specific example. And I know, learning to think on your own is tough. But it looks like to me the m's cancel. And I'm left with the acceleration equals g times the sine of theta, 2.6. All right, that's example number 2 for today. You ready for example number 3? I am. We're moving on unless somebody asks a question. I'm waiting, but make it fast. Okie doke. I'm no longer waiting. At the front of the room, I have a spring. It's just dangling there. However, I'm going to go and put a weight on it. Oops. And when I do, I'm just going to stretch the spring out. Let me show you. There's a spring on its own, not stretched. Put a weight on it. And now that weight's on it, clearly stretched. It stretches the spring 9.5 centimeters when I put 200 grams on it. What's the spring constant of the spring? I didn't teach you this one. This one you could be forgiven. It's on your sheet I handed you though, which I'm sure you've been studying. I'd hate to think that you were wasting the time I put in to prepare it for you. So anybody not reaching for their bag either doesn't have theirs or is too lazy to get it out. That's disappointing. Especially from homecoming court. You look so dapper. Do we have the results yet, or are they gonna make you guys wait till homecoming?
They're gonna make us wait till homecoming.
Oh, good. Hate to find out too soon. All right, so it stretched 9.5 centimeters when 200 grams was placed on the spring. If you don't know where to start, how about, is this a first law problem or a second law problem? This is a first law problem. Net force must equal 0. I guess I'll start by reducing my mass to a dot and deciding what forces are acting on it. Seems like an okay place to start. We are in the forces unit. I'm going to forego some of my normal questions. I'm going to draw a downwards arrow that indicates the force of gravity, mg, acting on the mass. And I think the spring is pulling up on the mass with a tension of, we'll go with T. T works for me. Does it work for you? Seems to me that the net force on the mass is going to be equal to 0. So tension minus mg equals 0. Nice stretch there. Keep that air flowing. Seems like I could probably say that tension equals mg. That good enough? What caused the tension? The spring. Springs are special because springs stretch in order to apply a force. In fact, this particular spring obeys Hooke's law, which means it's a linear spring. Now, I know you don't know what that means when I say linear spring. Some of you might. A linear spring means that the amount it stretches is proportional to the force. Let me ask you something. If I put 100 grams on the spring, how likely would it stretch? Half. That's what makes it a linear spring. Because it's proportional. If I double the weight, I double how much it stretches. If it was a different kind of spring that was non-linear, it wouldn't do that. But a linear spring is proportional. In fact, Hooke's law says that the force from the spring is proportional to the displacement. That's what Hooke's law says. It even tells me more than that, because it tells me that the direction of the force is opposite the displacement. If the spring stretches downwards, the force from the spring is upwards. Well, I think we could bring these things together. Don't you? The tension is caused by the spring.